Yeah, hi, thanks everyone. I hope everyone can hear me and see my mouse and my clicking as well. Okay, so if so, then I'll begin. Yeah, so thank you very much for staying until the end, and thank you to the organizers for giving me this opportunity to speak here. I'm very excited to share my most recent work done together with Soo-Won Choi on a new kind of non-equilibrium universality that emerges from quantum chaotic dynamics that goes beyond quantum thermalization, namely in the form of emergent quantum state designs. And if you don't know what this is, don't worry, I'll explain this to you in this talk. So just to set the stage, what we're interested in is universal behavior far from equilibrium. And I'm sure this audience in this crowd is familiar with the example of quantum thermalization. So a simple initial state undergoing time evolution, even in a closed many-body system, typically becomes a complicated entangled mass. And this depends on the precise microscopic details of the system. But we know that if we zoom in and look at local properties of a system, then something amazing happens where we can describe the system locally by some universal mixed Gibbs state that only depends on some local global properties like the temperature or the particle number of the system. So the question here is, what kinds of other non-universal behavior, universal behavior can emerge in non-equilibrium settings? And through this conference, we've heard of many examples like monitored quantum circuits, but I'll try to answer this from the point of view of reanalyzing or analyzing the assumptions that go into quantum thermalization. So precisely what happens is that if we're interested in a local subregion of a system, then we bipartition the system into two parts, A and B, and then we form the reduced density matrix by tracing out the degrees of freedom of B. And this B subsystem is taken to be very large compared to A, so we have the assumption that it forms a heat bath for A. And so explicit in this definition is the fact that this tracing out procedure means that we assume that the bath is inaccessible, or we are ignoring the states of the bath, and therefore we are only ever considering local measurements on A. So this framework is all fine and good, but let me now argue that actually a new generation of experimental platforms going in the form of like trapped ions, superconducting qubits, cold atoms, and so on, actually give you access to information that go beyond this formalism or framework. So in particular, in these experiments, what we have is the ability to read out the system globally, perhaps only in one basis, like the computational basis, but nevertheless, that means that we get access to correlations between the subsystem and bath, at least in one basis. So one can imagine that we can measure something like not just local observable on A, but local observable on A conditioned upon the classical state ZB of the bath. So here I denote this by OA as a function of ZB. And practically what you would do is that in these experiments, you just take many snapshots of the system, and then you just post-select your data to match the state of B to be one, say, bit string in which you've collapsed the bath into. And then you can measure this OA condition upon this classical state. Now we don't have to focus on one particular classical state. We can form the average over all classical states with respective probabilities, and we can form combinations such as this, which is linear in the classical state of the bath. But not only can we form this objects, we can also raise this to the power of k and form nonlinear observables, like raising this observable within each classical state to the power of k and forming this average. And my point is that in these experiments, you can measure such quantities which go beyond this formalism of the reduced density matrix. So the question we can pose here is, how then do we describe subsystems with some information of the bath? And this is the point of this talk, is to introduce this new framework and also to describe some new universal behavior in this framework that goes beyond quantum thermalization. So with that, the outline of my talk is as such. I'll describe this new framework. It's called the projected ensemble. Actually, I think it was mainly, it was introduced first mainly by Jordan Kotler and Soo-Won Choi, and also probed experimentally by Manuel Andres in Caltech. Well, the main idea is that from a single many-body wave function, one can obtain an entire collection of pure states on a subsystem that each of which are correlated with a measurement outcome on the bath B. Now, I will go into more detail in the next few slides. But from this ensemble, then we can describe some, I'll describe some observations of novel universality that has been observed, namely the fact that these states are they form truly hard random states, and this is what is known as quantum state designs in the parlance of quantum information theory. And I'll present to you an exactly solvable model in which we can exactly prove this statement. And time permitting, I'll talk about some applications in quantum information science, but let's see if I have time enough to get to that. All right, so with that, let's talk about this new framework. So the input is really a quantum many-body wave function. We can have it from a quantum circuit evolution, or in quench dynamics. It doesn't have to be from dynamics. We can take it to be an energy eigenstate, and very similar things as you do in quantum thermalization. So if you're interested in a local properties of a subsystem, we divide the system into two parts, A and B, as is done in quantum thermalization. But here's where we can make a departure from the standard framework. Let's assume that we have access to, that we can projectively measure the state of the bath in some local basis, and therefore obtain a bit string ZB. So for example, you might obtain this bit string of this bath, 1001000, and then we know that the system will then collapse to a state in which this part is definite, and this part is a pure state on A, which is potentially entangled, but is given by the Born update. And this occurs with the probability P that depends on the bit string ZB. And if we repeat the process, we might get a different bit string ZB, and we get different pure states. And all in all, what we have are 2 to the power of NB states induced by the bath, as well as respective probabilities. And this is what we can call the projected ensemble introduced by these two works. So the ensemble is denoted by 2 information, the pure state as well as its respective probability. And let me state outright that this is not your usual density matrix, a mixed state that you think about. The way that one can think about this is actually, in some sense, unraveling the effect of the bath in a local basis upon measuring it in a local basis. And therefore, it's very akin to like tracking each individual trajectory in a monitored quantum circuit. So with this in mind, now let's see how we can understand this projected ensemble framework. So how can we visualize it? For the case of a single qubit, this is we can easily draw it because a pure state on A is just a vector that points somewhere in the block sphere. So suppose that we measure this bit string ZB on the bath, we might get a state that points somewhere in the block sphere. You get a different state depending on the ZB that we measure. And if we keep repeating the process, we get a collection of states that point somewhere in the block sphere. Here I've drawn for you a cartoon in which the states are all pointing uniformly around the block sphere, roughly speaking, but they don't have to be. They could point somewhere in some direction along the block sphere. But the point is that we can see that this forms a distribution of states on the block sphere. And more generally, for the case of more than 1 qubits, this is a distribution on the hypersphere. So given that we have a distribution of pure states on the hypersphere, or more precisely, a probability distribution, of course, we can characterize it by looking at its moments. So, so for example, the first moment is obtained by taking each pure state, forming its density matrix, and then forming the average over all this density matrices with respective probabilities. And it's not hard to see that this is actually nothing more than the reduced density matrix on A. And therefore, this framework of projected ensembles recovers the standard treatment of quantum thermalization, which is good because then we have statements of universal behavior for the mean, at least insofar as we believe that ETH holds for cases like quantum quenches in quantum chaotic systems. But we also know that the mean does not fully characterize the ensemble or any distribution. For example, the maximally mixed state of rho A being proportional to the identity, which means that the center of mass of all the arrows is pointing right smack in the middle of the block sphere, could have many origins. It could be all the states pointing roughly uniformly around the block sphere. They could be concentrated along the north and south pole, or they could be lying in the equatorial plane. And so this mean does not distinguish between these 3 cases. Of course, the resolution is that we have to look at the higher moments, and this involves forming the replicated copies of the density matrix and summing over them in some ensemble fashion. And this is a higher ensemble density matrix. So at this stage, one very natural question to ask is, how can we characterize how random this distribution of pure states are? And so this is the question, how to quantify how random pure states are. And there's a very precise answer, quantitative answer from quantum information theory, which is to ask if it forms a quantum state design, or do these states, psi of A, mimic the action of Haar random vectors on the space A? So more precisely, here's a formal definition, but yeah, I'll just quickly run through this. So we say that an ensemble of pure states given by pure states and its respective probabilities forms a quantum state K design if any statistical property up to the kth moment cannot be distinguished from that of Haar randomly distributed states. So more precisely, what we do is that we form the kth moment of the ensemble. We form the corresponding kth moment of the Haar random ensemble, where the states are drawn uniformly from the Haar distribution. And then we can compute some sort of distance between them. It's not too important to know what the distance is, but this is given by the trace distance. And if you say that this distance is 0, then it forms an exact K design. And if it's epsilon, it forms an approximate K design. So this might be a bit technical, but colloquially, all I want to say is that a higher K design implies that the ensemble of states are increasingly uniformly distributed in Hilbert space. And that's the main picture that you should have in mind. So now let me just throw out some very key facts about quantum state designs. So a higher K design implies a lower K design, but not vice versa, quite naturally. And more importantly, well, not more importantly, but importantly, is a necessary condition for the number of states in an ensemble to be large in order to form an approximate K design, but it's not a sufficient condition. So precisely, it has to scale as dimension of the Hilbert space raised to the power of K. So for example, if I want to sample, why is it not working? Oh, sorry, it kind of hung. Okay, so for example, if I want to sample the space, the Hilbert space, and ask if the ensemble forms a approximate 1 design, I need, roughly speaking, to the power of n states spread around this Hilbert space. A 2 design requires to the power of 2n states, and so on. But we see that having many states is not a sufficient condition because they can be all concentrated along in some region of the Hilbert space and can be far from the design. Great. So now with that framework behind us, and this is a new formalism that we can try to compute in a physical system, we can ask a physics question. What do we expect to get from the projected ensemble from quench dynamics of a, say, generic quantum chaotic Hamiltonian? And this is the focus of these 2 works here. I'm not involved in them, but let me quickly run you through what they observed. So one was an experimental paper and one was a theoretical paper, and mainly numerics for this kind of setups. So in the numerics, they studied a mixed field Ising, which we all believe to be generic and quantum chaotic. And so the idea is that they begin with an infinite temperature initial state, infinite temperature insofar as normal ETH goes. They compute the projected ensemble, and then they compute the trace distance with respect to the Haar ensemble, and they plot it as a function of system size, how long the quench time is, as well as how many qubits they're measuring out, so the size of the buff. And this is what they see for a subsystem size fixed to be 3, and for increasing buff sizes from going from 9 to 21. And so let's not worry too much about the functional form, but the key point is that the trace distance goes down in time, and before it saturates for each system size, and the saturation value goes down with system size. And this is completely in line with our expectation that the reduced density matrix should become maximally mixed. So this is nothing more than just standard quantum thermalization, and this plot should not ever surprise you. So, but what do we see for higher moments when K is not 1? So qualitatively, they see very similar things, similar curves, also for 3 and 4. And these curves represent that there's physics that go beyond quantum thermalization, in which the ensemble of states that you get from subregion A is becoming more and more uniformly distributed in Hilbert space, or it represents the emergence of quantum state designs. And if you want to give it, sorry, my computer keeps jumping. So if you want to give it a fancy name, we can call this deep thermalization, because this is implying that there is thermalization not only at the level of local observables, but at the level of the wave function on the subsystem itself. So here, let me now describe some experiments. And so they performed some quench dynamics in Manuel Andres's group using a Rydberg atom array. Not too important to know what the exact Hamiltonian is, but it's very similar to the previous slide where they looked at quench dynamics of an infinite temperature state. And in the experiment, they can measure all these bit strings, which they get out globally. Now, in the data that they have, they post-process it, look at a particular bit string ZB. So they fix the outcome of ZB that they want, and they can plot, they can obtain the probabilities of measuring a bit string ZA on this subsystem A. So in doing so, what you end up with is the projection of the projected state onto some bit string ZA. For example, if ZB is all zeros, then you might get such a distribution. For a different bit string ZB, you might get a distribution, and together you can plot, for example, the distribution of the probabilities themselves and ask, or more precisely, compute a histogram of the probabilities. And this is what they see. So the bars represent the experimental data, and they see that that this forms this characteristic curves for different system size A's that they're measuring. LA is 2, 3, 4. So this black line does not represent a fit function, but actually represents the exact theoretical result, no fit function, if you assume that the states from which you're obtaining the probabilities were truly Haar random in nature. And we know, we know that this distribution is actually the Porter-Thomas distribution, a very famous Porter-Thomas distribution, which, sorry. Oh, I removed the slide. Okay, which I should say that Google used to try to understand if the quantum circuit tended towards in order to prove a statement about quantum supremacy. But in our case, this is not about quantum supremacy, but at least this shows that the projected states on the subsystem A are statistically indistinguishable from high random states insofar as Z projections go. So now to answer the question initially posed, what physics do we see from the projected ensemble? We can make the observation supported a lot by numerics and that go beyond the model I talked about, and also experiments that seem to see that at least for initial states at infinite temperature, there seems to be an emergence of pseudo-random states on the local subsystem generated by the bath. And we can call this deep thermalization, or in the parlance of quantum information theory, the emergence of quantum state designs. And this is a new kind of random matrix universality in which we have random vectors emerging from the local subsystem. So the question I want to pose here is, can we, well, find an exactly solvable model that exhibits this phenomenology and therefore nail it down and show that this definitively happens, at least in some model. And in doing so, can we understand the mechanism behind this emergence? And that's the basis of this work I'll describe in the next half part of the talk. Okay, so the model is actually, I would say, perhaps quite familiar to many of you. It's not surprising to learn that this model is the one-dimensional periodically-kicked Ising model, which is a Floquet model. It comprises of two parts during each Floquet cycle UF, application of two unitaries U1 and U2. U1 is nothing more than Ising interactions plus longitudinal field, and U2 is a transverse kick, which I denote to be in a y direction, but this is not too important. So the longitudinal field is given by a strength G, Ising interactions J, and transverse kick by H. So now what we can do is that we can look at time evolution up to some Floquet time t, where t is integer valued, so how many applications of UF. We divide the system into two parts, NA and B, and let's measure the system in the Z basis for this NB region, and the initial state is everything polarized in the plus state. So the punchline is this, and let me state the result that we have in our paper. We can prove rigorously a statement saying that if we let the Ising interactions be pi over 4 and transverse kick be pi over 4, which are special values, but we allow for arbitrary G, longitudinal field, excluding some special points in which they are integer values, integer multiples of pi over 8, then we can show that in dynamics, when the number of Floquet applications T is greater than or equal to the region of interest, so T greater than or equal to NA, the resulting projected ensemble forms an exact quantum state design in the thermodynamic limit. So the catch is that we have to take the number of qubits that we're measuring to be infinite. So more precisely, we can match every moment of the ensemble with the hard random ensemble, every kth moment. So let me take a slight pause here, because I should say that this is I believe to be quite a remarkable result, because if you think about it, this time needed for you to form truly random hard states, well, truly pseudo-random hard states that you cannot distinguish from hard random states, only takes finite time in the total system size. So you don't have to evolve time that is proportional to the full system size. So in particular, the state that you get at the end of this evolution is just every law entangled. Nevertheless, measurements induce for you a whole collection of truly pseudo-random states that you cannot distinguish from high random states. And I think this is remarkable. So just to show you some numerics, if you don't believe the theorem. So here's what we can see numerically. So I take a subsystem size of 3, and then this is the emergence of the state designs in time, quench time, and also how many qubits I'm measuring. So in the top panel, I am fixing the number of qubits I'm measuring to be 100, and the different colors represent different moments. And we see that initially the trace distance is far from 0, so they're not maximally entropic states. But then over time, this goes down, and magically all the moments hit 0 exactly at this critical value of time 3, because NA is 3 in this case, and they will stay to be 0 afterwards. Now we see the convergence with respect to the number of qubits measured is exponential. So for the first moment is special, and this was proven by Tomesh. why this is special, but for the other moments, we see that this convergence to the quantum state K design is exponentially fast in the number of qubits measured. So in the next few slides, let me now try to sketch for you an idea for why this happens in this model. And this might be a bit technical, so I apologize if so, but I hope to give you a flavor of the proof so we can understand what's going on. And then I will take a step back towards the end so that we can summarize and understand what we have just learned. So the key property is that we'll use is the dual unitarity of the model. So at the special values that I pick when J is pi over 4 and H is pi over 4, we can exchange the role of space and time. And this was, I believe, what Thomas talked about earlier today, about how to prove that in this model as well, that you have random matrix theory spectral form factors that match exactly with the RMT predictions. So by exchanging space and time, we can perform computations either way. And in our case, what that amounts to is that if you're looking at the projected state obtained from Fouquet evolution, we can equivalently think of this as appearing from an evolution of a fictitious spin chain in the temporal direction by a sequence of unitaries, u to the 0, u to the 1, and so on. And this sequence of unitaries, they only come in two flavors, u0 and u1, and they depend on the measurement outcome that you measure at the end result. So you see that this measurement outcome 0 corresponds to this evolution and so on. And towards the end, there is a mapping that maps you from the fictitious space towards the actual space. And this is not too important, but suffice to say, this is an isometry. But now the key point is that I just want to make is that the measurement outcome in the real picture or the original picture given by a sequence of numbers, 0, 0, 1, 1, binary numbers, actually determines evolution in the dual direction, dual picture, by a random binary quantum circuit built up of two basic building blocks, U0 and U1. So our task really becomes, so like the main picture here is that we can think of this as a quantum computation in the dual space. We can think of this as the state that emerges here arises from some sort of quantum computation determined by the measurement outcome ZB. So we now have to understand exactly what sorts of quantum computations this quantum circuit is doing. And so let me just state that U0 is actually nothing more than the original Fouquet unitary, but acting now on T fictitious qubits. U1 is pretty much the same, except for a seemingly innocuous change where there's an extra Zeeman field action on the boundary, specifically of a strength pi over 2. So this one very small change means that actually gives rise to a whole family, a whole host of differences, because now this becomes a evolution by a randomly kicked Ising model. And by randomly kicked, I mean that this is the kicked Ising model, but at every point in time after you kick, there's a chance that you encounter an extra field, so the field is fluctuating here. And this randomness in time is actually ultra localized because it's only on the last site of the system. Here this is the index T. So the claim we can make actually in our paper, and we prove this in our paper, is that if we look at the limit of large depth of this quantum circuit, it turns out that these quantum circuits, if you consider them as a whole, they are statistically indistinguishable from Haar random unitaries, i.e. they form a unitary design. And more prosaically, what that means is that the more important feature, what that means is that if we start out with any, say, reference state in the many-body Hilbert space, and we're trying to go to a different state here, you can always find a ZB that maps you from this state to this state. So for example, like if you, crap, sorry. Yeah, so if you want to go to this other state in the Hilbert space, there exists another ZB that maps you to this point. So the point is that these quantum circuits are dense in the space of all unitaries. And if this is correct, sorry, the computer is lagging. If this is correct, then that means that these quantum circuits imply that the projected states are uniformly distributed in Hilbert space. So the main point that we have to understand is, so in doing so, then we would have proven our theorem. But the main point that we have to understand next is to understand why this is correct, why this quantum circuits are indistinguishable from Haar random unitaries. So to do that, we can compute the kth moment of the Haar random unitary ensemble, and ask if it matches with that of our actual unitary circuit ensemble. And so yes.
You should finish in a few minutes.
Yeah, I'm almost done. Yeah, So in doing so, we're trying to match these two moments, and so we can represent them in some pictorial diagram. And the key point here is that we can understand it as the evolution, a transfer matrix raised to a high power, where the transfer matrix has two parts, projector and unitary, and this projector is actually a dephasing channel on the boundary. So from this form, we see that the transfer matrix, being a product of unitary and projectors, has eigenvalues which are less than or equals to 1, at least the modulus of it. So we only have to understand which ones survive in the thermodynamic limit once we raise this to high power, because those are the ones with eigenvalues 1 are the ones that survive. And so this is a bit technical, but let me just quickly run you through. So we're interested in eigenvectors A that satisfy this condition being unimodular. So this is absolute value 1. There are some conditions that we can write on this state A, and then we can invoke an operator state correspondence to say that actually, if we now think of the state in the replicated space as an operator, then there are some conditions that need to be satisfied on this operator. And you can see that A has to commute with such a unitary, and A has to almost commute with the Fouquet unitary as well. But from these, we can actually define a lot more constraints on A, and say that not only do these two conditions need to be met, A has to commute with a lot of other unitaries, VP, formed by some definitions of UFs and Zs. So the point here is that what constraints does A need to have? So it turns out that A has to commute with every unitary in a unitary group. And now we can invoke a very interesting result from representation theory, which is a Schur-Weil duality, which says that any operator A which commutes with any unitary tensor product to the raised to the power of K is always spanned by permutation operators that act on a replicated space. And we see that now we have proven that the kth moment of the Haar randomly generated ensembles is the same as that of our ensemble. And this is the origin of universality. So because I'm running out of time, so let me just quickly state that, so if that was too technical, the main result that you should just take home is that for this model, we can exactly prove this result, that the distribution of states on the Haar random, on the projected ensemble is identical to the Haar random states. And this happens in finite time, which is a pretty remarkable thing. So to summarize, so I've introduced to you a new framework called the projected ensemble, states arising from measurements of the bath that live on the local subsystem. And within this framework, I've described to you some new universality, the emergence of quantum state K designs, or the fact that these states are pseudo-random in nature. I've proven for you a situation in which this happens. And I did not really talk about this, but this is interesting because it provides a new perspective towards quantum thermalization, towards quantum chaos, in which the randomness happens at the level of a single many-body wave function and not necessarily at the level of, say, the energy spectrum or collection of Hamiltonians. And this is a new perspective. And so for outlooks, I've mainly focused on infinite temperature initial states. And so it'd be interesting to ask if there are similar concepts for initial states which begin at finite temperature, what universal ensembles would they go towards? And in quantum information theory, there are connections between formations of quantum state designs and quantum complexity, which I think we should explore here. And perhaps this can also be used as a test of quantum supremacy in near-term quantum devices. And I didn't have time to talk about this, but there are many applications in quantum information science that requires the generation of random ensembles of states and unitaries, for example, like tomography, benchmarking, which can be developed using such a method. So with that, let me just quickly flash out an advertisement saying that beginning the fall of 2022, I'll be beginning my group in the National University of Singapore. So if you know of any interested grad students or postdocs interested in working at the interface of condensed matter, AM, or quantum information science, please don't hesitate to ask and contact me. So with that, thank you very much. And let me flash out my summary slide, and thank you. And I'll take questions at this point in time.